Hi, I'm Victor Costa and I'll present an exploration of a low-power CMOS Voltage Squarer. The other authors of this paper are Adilson Cardoso, Cesar Rodrigues, André Aita, and Jefferson Marques. This research was conducted by both Universidade Federal de Santa Maria and Universidade Federal de Santa Catarina. This interest in exploring voltage squarers comes from the fact that they have many applications. For example, in signal processing, they can be used in the context of peak detection for biomedical circuits, or even power estimation of a given signal in continuous time. We begin this exploration by analyzing a voltage multiplier proposed by Chen and Li in 2006. We specifically choose this structure because the authors have compared it to the most recommended structure in a review of voltage multipliers made by Han and Sanchez-Sinencio. And the authors, in this case Chen and Li, have shown that the multiplier in the schematic I'm showing here achieves a power dissipation of at most 1/3 of the most recommended structure by Han and Sanchez-Sinencio. In the schematic shown here, uppercase letters X and Y represents bias voltages, and they must be chosen in such a way that the PMOS devices, that is P1, P2, P3, and P4, operate in saturation region, while all other devices, that is NMOS devices, operate in triode region. The small case letters X and Y represent signals here, that is differential signals, and the circuit is considered a fully differential circuit because not only its inputs are differential, but also its outputs. The authors of this multiplier join transistors in groups P, N, and M. The transistors within the P group are all PMOS devices, while transistors in groups N and M are NMOS devices. Within each group, the transistors have the same aspect ratio, and based on this grouping, the authors propose the following transfer function, in which the circuit's differential output is proportional to the multiplication between differential signals times this ratio. In this ratio, the K constants are proportional to carrier mobility, to the gate oxide capacitance, and to the aspect ratio of each group. To demonstrate the behavior of the circuit, we can let Y be a constant and then plot the differential output as a function of X. Here, we can see how we can increase the slope of the output by increasing the aspect ratio of PMOS devices. We can reach the same conclusion by computing the gain of the differential output with relationship to one of its inputs. Here, we can see that, according to this original transfer function, if we keep Kp constant, the gain should also remain constant as long as the Kn-Km product remains constant. But as the tables here shows, in which we keep the Kn-Km product constant, we can see that the maximum slope of the differential output does not remain constant. Therefore, this shows that the original modeling of the circuit is inconsistent, and therefore we do not use it here forward. We do use the following logical relationship, in which the gain will increase with increase in the aspect ratios or the overall K constant of devices in saturation, and the decrease of the K constant of devices in triode region. As done multiple times in the past, we can employ a multiplier circuit as a squarer by simply providing the same signal, in our case Vi, for both of the multiplier's inputs. In this case, we can have the following transfer function for a multiplier circuit, and when we consider, of course, the DC level of the output. And we can observe that the same gain we find in the multiplier normal operation is carried for the multiplier with a squaring operation. In the case of the baseline multiplier, here we can see both single-ended outputs and the differential output in blue. Differently from the linear case, here in this squaring mode, one of the outputs, the VO1 single-ended output in red, is kept at an almost constant value. To compare the single-ended output VO2 with the differential output VO, we must first define this notion of a nonlinear or second-order gain. We have seen previously that this gain of a square circuit is equivalent to the gain of the multiplier, but here we can see that to compute it, we must take the second derivative of the output with respect to the input. Since here we are dealing with practical and not ideal square circuits, it's expected that this gain, or nonlinear gain, will suffer some deviation from its maximum value in the presence of a signal. Here, in this plot, we can see the deviation which the differential output suffers in red in the presence of a signal Vi, and the deviation which the single-ended output VO2, shown in blue here, suffers in the presence of a signal. And we can see that the deviation of the differential output is larger and gets even larger in the presence of a signal with higher amplitude. This then justifies the use of the VO2 output as a squarer instead of using the whole structure, because we not only improve this deviation from the maximum second-order gain, but we also need only half of the circuit, and this will cut by half the area we need to implement it and the both static and dynamic power dissipation. The schematic of the baseline multiplier confirms this by showing us that the subcircuits that generate outputs VO1 and VO2 are completely independent of one another, but when we discard VO1 and use only VO2, the circuit is not differential anymore with relationship to its output, and then we will have the presence of a DC offset in the output. Because of the relationship we've shown between the gain of a multiplier acting linearly and the gain of a multiplier acting as a squarer, we can use the same logical relationship which says that to increase the gain, we must increase the K constants of the devices operating in saturation or decrease the K constants of devices operating in triode. But when we have the same aspect ratio for all devices, we can see that since the carrier mobility of holes in PMOS devices is lower than the carrier mobility of electrons in NMOS devices, the Kp, or the K constant of PMOS devices, is lower than Km and Kn, and therefore the K value, which should be larger to increase the gain, is smaller, and the K value, which should be small to increase the gain, is larger than the other. So in this case, we have an intrinsically low gain. To circumvent this problem of a low gain, we then propose a complementary version of the baseline squarer, and we call it an inverted squarer. In the circuit, we have NMOS devices operating in saturation and driving the circuit's current, while PMOS devices in groups P and Q operating in triode. We still have the same logical relationship as before between K's and the gain, in which a higher K for the devices operating in saturation and a lower K for the devices operating in triode leads to a higher gain. But since in this case the K of devices operating in saturation, when we have all the devices with the same dimensions, is higher than the K of devices operating in triode because of the difference between mobility values of electrons and holes, we have an intrinsically higher gain when compared to the baseline squarer. Due to this difference between the baseline and the inverted squarer, within the same power budget, we can obtain a gain boost of more than 10 times when using the inverted squarer. To show this logical relationship between case and the gain in practice, to see this relationship in practice, we can plot the transfer function of the inverted squarer as well as its nonlinear gain. Here we can see that increasing the Wn variable and therefore the Kn will cause an increment in the absolute value of the gain, but also it will cause a decrement in the maximum allowable range of the input signal. This increment in gain comes with an increment in the circuit, since the NMOS devices drive the circuit's current, and therefore we have a power gain trade-off here. We could repeat this analysis for the Kp and Kq parameters, but instead of seeking higher case, we would seek lower case, and these modifications would not change the circuit's current and we wouldn't affect its power, but we could increase the L parameter of each device in these groups to obtain a higher gain, and therefore we could have a gain area trade-off. And to explore this gain area trade-off is precisely what we do in our case study. Since we can't decrease the KQ or KP values under a certain threshold because of the design rules provided by foundries, we then duplicate these Q devices in such a way that we artificially augment its L values and then decrement the joint KQ, first to say. The high gain we achieve with this structure also has a negative consequence. That is, when we simulate process corners, the transfer function highly deviates from the nominal operation of the circuit. This happens because our structure is highly sensitive to variations in threshold voltages of PMOS and NMOS devices. To ameliorate this situation, we employ a bias circuit which is also sensitive to these variations in threshold values of PMOS and NMOS devices, and therefore it counterbalances this negative effect and we reach a much better response in the presence of corners.
To analyze the impact of mismatch within each device group before we lay the circuit out, we have run Monte Carlo simulations using the statistical parameters provided by foundries. When we isolate the effect of mismatch in the group of devices N, we have a standard deviation of the output DC voltage of 3.45 millivolts. In the case of the Q devices, we have a standard deviation of 0.3 millivolts approximately, and in the case of P devices, we have a standard deviation of 3.6 nanovolts. This is evidence that the group of devices N is more sensible to mismatch than the group Q, and that the group P is much less sensible than both of them. When we run Monte Carlo simulations for process variations, we can see its effect over the output DC voltage. Here, we can see that for an interval of 2 sigma, we have a variation of approximately 5% when we consider the mean. Here, we can see how the circuit was laid out. We only highlight the active devices and all others are dummies. For the severity of mismatch in NMOS devices, we surround it with 8 dummy devices, and we also put the bias circuit in the same layout so it suffers the same process variations of the main circuit. When we compare the DC response of the schematic versus the layout, we have basically a difference of 10 millivolts between each of them, and this is caused by a difference of 3 millivolts in the output of the bias circuit. When we compare the square circuit of our case study against other voltage squares in the recent literature, we can see that it has the smallest area amongst the reported ones, given the same technology node. And when we compare it power-wise, we can see that the 0.5 microwatts power dissipation, static power dissipation of the main circuit is only higher than the static power of configuration 1 in reference 10. For the other configuration, we have a much lower power dissipation, and for both configurations, we have a higher gain, much higher gain.